Welcome to Lecture 9 of the Wireless Communication course at Chalmers University of Technology. My name is Henk Wemiers. In this lecture, we will learn about multi-user communication, about uplink, downlink, multiple access, and random access. We will discuss TDMA, FDMA, and CDMA. We will also design and analyze multiple access schemes for given scenarios to meet certain SAR and SANR requirements. We will cover several chapters, or at least parts of several chapters of the book, as shown in this slide. Last time we saw that if we want to increase the data rate, we have two options. One is to use higher order modulation formats, send more bits per symbol. The other is to use more bandwidth and send our symbols faster. This is limited by intersymbol interference. In order to avoid complexity-hungry equalization methods, we introduced OFDM, which is based on fast Fourier transforms and a cyclic prefix, in order to trick the receiver into thinking that we're sending a periodic sequence. We saw that for a fixed sampling time, the duration of the cyclic prefix should exceed the delay spread of the channel, and that the OFDM symbol duration should be much less than the coherence time in order for having the same channel over one OFDM symbol. OFDM creates parallel channels in the frequency domain and can thus be easily combined with water filling if channel state information at the transmitter is known. An important drawback of OFDM is peak to average power ratio. At the receiver side, for a certain OFDM symbol with index m, we will obtain a number of samples, a few corresponding to the cyclic prefix, which we discard, and then n samples we use for further processing. In these n samples, if the cyclic prefix is sufficiently long, it appears as though an infinitely long periodic sequence was transmitted. An OFDM transmitter operates as follows. We take QAM symbols, which we convert from frequency to time domain. So the QAM symbols reside in the frequency domain. We have time domain samples. We add a cyclic prefix and send over our channel. So the duration of one OFDM symbol is the number of subcarriers n plus the cyclic prefix times the symbol duration. The cyclic prefix leads to a certain overhead, which we try to minimize. We can minimize this overhead by having relatively long OFDM symbols with respect to the cyclic prefix duration. At the receiver, we take our incoming waveform, sample, remove the cyclic prefix, convert back to the frequency domain, and demodulate. If the channel is constant for one OFDM symbol and the cyclic prefix exceeds the delay spread of the channel, we find that at the output of the OFDM system, in the absence of noise, the observation on a certain subcarrier is equal to the transmitted QAM symbol on that subcarrier and a complex scaling. This avoids the needs for complex equalization. So far, everything in this course related to single-user communication between one transmitter and one receiver. In practice, there will be multiple users that share the same physical channel, so the same time-frequency resources. This means that the communication should be coordinated. There are, broadly speaking, two types of communication systems: cellular and ad hoc. Ad hoc will be referred to later in this lecture, but let's first talk about cellular. In cellular, we have two types of nodes. One is the base station, the other one are the mobile users. We call the communication from the base station to the mobile downlink communication. The communication from the mobile to the base station is called uplink communication. This difference is shown below. In the left side figure, we have the base station transmitting signals to different users over an individual channel per user. Each user sees the transmitted signal convolved with the channel plus additive white Gaussian noise. In the uplink, on the other hand, each user sends an individual signal, so the signal depends on the user, over the channel again, and then the signals are added up plus noise. So the receiver sees the superposition of the signals coming from the different users, each convolved with their own channel and one additive noise. We recall that for single-user communication we had the following scenario. We have a transmitted complex baseband waveform, which comprises an infinitely long sequence of pulses s of t, each spaced a symbol slot duration ts apart. Ts is approximately 1 over the bandwidth. and for each pulse we send a symbol AL, for instance drawn from a QAM constellation. We can rewrite S of t minus LTS as S subscript L of t. Okay, so this is just a different way of writing the same thing. The observed signal Y of t is then given under flat fading as a complex channel gain alpha times the transmitted signal plus noise. We would then apply a match filter plus symbol rate sampling. This is equivalent to generating an observation ZL, which we would like to recover AL from, given by the received waveform multiplied by the complex conjugate of SL of t and then integrated. So we can see this as a projection of YT onto SL of t. If we substitute Y of t back, we find the complex channel gain, an infinitely long sum over all possible transmitted symbols, and then the integral of SL prime of t times SL of t. So this is a projection of SL prime of t onto SL of t. If the waveform is designed according to the Nyquist criterion, this integral will be 0 when L is different from L prime and 1 when L is equal to N prime, plus a noise sample. Under the Nyquist criterion, we thus recover the complex channel gain times the transmitted symbol at time L plus white Gaussian noise. The first problem that we face is called duplexing, which is the separation of uplink and downlink transmissions. Clearly, uplink and downlink cannot be in the same time frequency resources. There are two ways to separate uplink and downlink. One is FDD, frequency division duplexing. In FDD, we have an entire frequency band available, which we split up into an uplink band and a downlink band. In between, there can be a guard band. All uplink communication happens in the uplink band, while all downlink communication happens in the downlink band. Of course, within, for instance, the uplink band, we still need to assign resources to different users to allow uplink communication. A second approach is called TDD, or time division duplexing. In time division duplexing, we allocate certain amounts of time for downlink transmission over the entire frequency band. Other times are used for uplink transmission, again over the entire frequency band. In between uplink and downlink slots, we have a guard time. These are some of the properties of TDD compared to FDD. TDD is better for asymmetric traffic. For instance, if users tend to download more than upload, we could make the downlink slots longer than the uplink slots. TDD will incur delays. This is because when a user wants to upload something, it needs to wait till the next uplink slot becomes available. TDD also requires synchronization between the users and the base station. Finally, TDD is able to exploit uplink-downlink channel symmetry. This is because when an uplink and downlink transmission occur within a coherence time, after an uplink transmission, a base station will have knowledge of the downlink channel, so it can use this information to transmit in a smarter way, for instance using adaptive resource allocation strategies. This is typically not possible in frequency division duplexing because uplink and downlink band are further away than one coherence bandwidth. Once we have decided on a duplexing scheme, we are then looking at the multiple access problem, which involves creating dedicated channels for users. Since we have time frequency resources to play with, this forms a natural basis to separate users. A first scheme is called frequency division multiple access. In this case, each user gets its own frequency channel that it can use for as long as it wants. So it has one frequency channel available for all time. This frequency band here, the total band could be the whole uplink bandwidth. There are two versions of FDMA, analog FDMA and digital FDMA, called OFDMA. In OFDMA, we have a large OFDM system where different users simply use different sets of subcarriers. Conversely, we have time division multiple access, where each user gets a time slot, for instance here for user 1. It can use this time slot over the whole frequency band, for instance the whole uplink band, but then needs to wait till it gets another time slot sometime later. So again, user 1 has another time slot here. Finally, there is CDMA, for code division multiple access. In CDMA, a user can transmit all the time over all frequencies, but has a specific code which allows it to not interfere with other users. TDMA, FDMA, and CDMA can all be written in one mathematical model. We will assign a unique waveform for each of the users, and we will then make those waveforms approximately orthogonal. This is written through this integral. Here, skl of t is the waveform of user k at time L. When we then multiply with the complex conjugate of sk prime L prime of t and integrate, we obtain a real number. We want this number to be small, so approximately 0, for two different users, so k different from k prime. This means that different users will not interfere. They will not see each other when we project. Similarly, when L is different from L prime, we want the integral to be 0, so that signals from different symbols for a given user do not interfere. We only want this integral to be 1 for k equal to k prime and L equal to L prime. The first condition ensures that there is no inter-user interference. The second condition ensures that there is no inter-symbol interference. Mathematically, we can then write the signal overall for user k as xk of t. It comprises an infinitely long stream of symbols. AKL is the L symbol of user k, and SKL is the waveform used to carry that symbol. For instance, in TDMA, users have separate time slots. It is immediately obvious that when we integrate the signal of user 1 multiplied with the signal of user 2, we obtain 0. So this condition is met for k different from k prime. In order to meet the condition for L different from L prime, the pulses for each user should be designed appropriately. Similarly, for FDMA, when we multiply the signal of one user with another user in the frequency domain, we see that the integral is 0. This also means that this condition is satisfied for two different users. TDMA and FDMA are two ways we can create orthogonal waveforms between users. However, the choice to divide up time or frequency is arbitrary, and we could develop other kind of waveforms where users are still orthogonal, but each user can use the entire time and frequency. CDMA is one such way, where users are assigned orthogonal codes. One version of CDMA is called direct sequence CDMA, in which we will spread out the symbols of the users. Let's consider user 1 and user 2. User 1 and user 2 each want to send one QAM symbol, their own QAM symbol, but to do that they will use 4 symbol slots. So user 1 will use 4 TS, user 2 will use 4 TS to send a single symbol, but they will use different codes. The code for user 1 is 1, 1, 1, 1. The code for user 2 is 1, minus 1, 1, minus 1. At the receiver, we will decorrelate with each of these codes to obtain the signals for each of the users. This is possible because these codes are mutually orthogonal, because 1 times 1 plus 1 times minus 1 plus 1 times 1 plus 1 times minus 1 is equal to 0. So from the point of view of a receiver, the two signals can be completely recovered. If a third user is here with a code minus 1, 1, minus 1, 1, then this user is orthogonal with user 1. Okay? So user 1 and user 3 could send simultaneously to a receiver, and the receiver, by correlating with the user's code, can recover the data from user 1 and user 2. However, user 2 and user 3 are not orthogonal. This is because 1 times minus 1 plus minus 1 times 1 plus 1 times minus 1 plus minus 1 times 1 is equal to minus 4. So these two users are not orthogonal, so they should not coexist. An alternative is frequency hopping. Typically, even when codes are designed to be orthogonal, they are often not orthogonal in the uplink due to delays, because the signal of different users will have different propagation delays. Let's look at this in more detail. We start with the easy case, downlink. In downlink, a signal S of t is sent from the base station to all of the users. The signal S of t is a superposition of the signals intended for each of the users, and the signal intended for user k is xk of t. xk of t involves QAM symbols, xkl, as well as a user-specific waveform, skl of t. At the receiver of user k, we obtain Rk of t, which involves the channel alpha k, the transmitted waveform S of t plus nk of t, the noise. The receiver of user k then performs a projection operation. So for symbol L, it will compute RKL, which is the received waveform projected onto SKL. We substitute all of the waveforms and then we find the result on the second line, which involves an infinitely long sum over all possible transmitted symbols, an integration of waveforms for user k, for L prime and L, and a summation for the other users, where we project the waveform of user k prime with respect to the waveforms of user k. The first integral is 0 except when L is equal to L prime. This is through proper waveform design for user k. So there is no intersymbol interference, all that remains is the alt symbol of user k. The second term is a so-called multi-user interference. The third term is the noise. The multi-user interference is by design 0 for TDMA and FDMA, as well for CDMA with orthogonal codes. In general, in CDMA, we will have a cross-correlation function, which is defined as follows. If we have orthogonal codes and we evaluate this cross-correlation function for a multiple of Ts, we will find 0 except for tau equal to 0. However, in between, we can have a non-zero value. Now we look at the more complex case of uplink. In uplink, each user wishes to transmit a signal to the base station. The signal transmitted by user k is xk of t. It involves its own symbols and its own waveform. The receiver sees the superposition of all of the waveforms from all of the users, each waveform with its own channel, and also the signals from different users are delayed. This is because different users may be at different distances from the base station or maybe transmitting at different times. We again project, so if we want to recover the alt symbol of user k, we will compute RKL by taking the waveform and projecting onto SKL of t minus tau k. Note here that we must account for the delay of user k in the projection operator. We substitute back all of the waveforms and we find again three terms. The first term relates to intersymbol interference. We see that this first term is 0 when L is different from L prime, and only L equal to L prime remains, so we recover AK times AKL. This is the first term. The second term is just noise. The last term is the multi-user interference. So we have a sum over all the other users with their channel, and then we have projections of waveforms between different users and different times. Again, note that here we have the delay for user k prime and the delay of user k. In terms of multi-user interference, so the last term, we see that under FDMA there is never any multi-user interference. This is because the waveforms between different users remain orthogonal no matter what these delays tau k and tau k prime are. This is however not the case for TDMA. For badly chosen tau k prime and tau k, the waveforms can overlap and they will no longer be orthogonal. Under TDMA, we will only have orthogonal waveforms between the users at the receiver side under proper timing advance. So the base station needs to tell the users when to transmit in order to avoid interference at the receiver. Under CDMA, we will always have residual interference. So we can never get rid of this interference because of the delays that can be any value here, tau k and tau k prime. This is especially harmful under so-called near-far conditions, in which there is one user that is near to the base station and which drowns out the signals of the other users. In case there is residual interference, the base station can resort to so-called multi-user detection, in which it tries to recover all of the signals even when they interfere. What it could do, for instance, is from the waveform first recover the signal from the strongest user and then subtract this from the received waveform, after which we only have a superposition of the remaining users. It can then proceed in the same way. We also note that the base station recovers RKL for all k and all L. So the base station is interested to recover the transmitted signals for all of the users for all of the times. This is different from the downlink, where a user is only interested in its own symbols for all times. Let us now look at some performance metrics for multi-user communication. So this is our now generic observation model. The signal received for user K at time slot L is the useful contribution, plus possibly inter-symbol interference, plus possibly multi-user interference, plus noise. So we have three parts: useful, interference, and noise. We now compute different performance metrics. One is SNR. SNR is a standard metric that we've used before for single-user communication, where we just take the ratio of the signal power divided by the noise power. This is a useful metric when the inter-symbol interference and the multi-user interference are negligible with respect to the noise. This is the so-called noise-limited regime. If we also want to account for the inter-symbol interference and the multi-user interference, we will compute the signal to interference plus noise ratio. So we will compute the noise power added to the interference power, and this will be our overall noise contribution. We can then use this SANR expression in error probability expressions. So this allows us to compute bit error rates and symbol error rates at least approximately in the presence of interference. This somehow assumes that interference is approximately Gaussian. Finally, we can also introduce the signal to interference ratio. In this case, we just look at the interference power and ignore the noise. This is useful for the interference limited regime when the noise is much smaller than the interference. These performance metrics are used to analyze the performance of communication systems for multi-user settings. They are also interesting for cellular communications. In cellular networks, there is communication between users and base stations. There is also a central controller that connects all of the base stations. A base station serves a certain cell, and a user is typically associated with a single base station. However, users monitor multiple base stations for so-called handovers. This is shown in the picture of the right. The red dots are the base stations. The regions around the base stations are the cells, which can be of different size, and the user is shown with a green path. As the user moves, it sees different cells and it needs to keep track of which base station is assigned to each cell. It does this by measuring power levels with respect to different base stations and then changing base station as needed. The placement and density of base stations is important because it creates a trade-off between interference and rate. More base stations is good because then you will have a higher chance of being close to a base station, but this can also lead to more interference from other base stations. One way to allocate channels to base stations is to provide them with unique frequencies which can be reused for base stations further away. One abstraction for this is to use hexagonal cells with periodic reuse. The figure on the right shows a hexagonal tessellation of the plane. We see a large number of so-called hexagonal cells. Each cell is associated with a single base station. Each cell has a label which corresponds to the channel that is used by this cell. So this could be a frequency band. In this case, all the cells that have label C1 use the same frequency band. We allocate those frequency bands according to some predefined algorithm, which in turn induces a clustering. We see in yellow a cluster of cells that use all of the available frequency bands, and this cluster is then repeated over space. We see that for a given cell size R, we have then an induced reuse distance. This is the distance between two cells that use the same channel, or the minimum distance between two cells that use the same channel. From this, we can then define the so-called reuse factor, the number of cells per cluster, in this case 19. This number is proportional to the reuse distance squared over the cell size squared. In the extreme case of a so-called reuse 1 system, all of the cells use the same frequency. In this case, n is equal to 1, and the cell size is equal to the reuse distance. We can also compute other metrics, for instance the cell edge SIR. This is the signal to interference ratio seen by a user on the boundary of the cell. For such a user, the power with respect to the home base station will be the lowest possible value, and this user will see interference from 6 neighboring cells that use the same channel. In principle, there is also interference from further away cells with the same channel, but we ignore those because their power will be very low due to the path loss. Ignoring shadowing and other effects, the signal to interference ratio is given by this expression. It is the power from the home base station divided by the interference power from the 6 interferent base stations. It is easy to show that this then leads to approximately a value of R over D to the power minus gamma. We now see an immediate relation between the reuse factor and the SIR. It follows that up to a scaling, the reuse factor should be greater than the SIR to the power 2 over gamma. So this allows us, if we have a certain target signal to interference ratio, to say what should be the reuse factor, and then this will tell us how many channels we would need to cover the whole plane. We also introduced the user capacity. This is the number of active users that are in a cell. So if you have a total bandwidth B and a reuse factor of n, then each cell will have a bandwidth available of B over n. Let's say each user uses a bandwidth Bs, then the number of users that we can support in a cell is the total per cell bandwidth, B over n, divided by the bandwidth per user. So we see that with a larger reuse factor, we can support fewer users per cell. We also have the system capacity. This is the number of users per unit area, or the number of channels per unit area. This is just the number of active users in a cell divided by the size of the cell, up to a constant. This, by substitution, gives us this result. So we see that if we want to increase the system capacity, we should make smaller cells or have a smaller reuse factor. However, if we have a smaller reuse factor, that means we have more frequency reuse, we'll have more interference. In modern systems, it is often desirable to have a very small reuse factor. So let's look at an extreme case where all the cells use the same frequency. We focus on the uplink case. So users are transmitting to their base station. For a user, it is advantageous to use a higher transmit power because this can protect against the effects of the channel and lead to a better SNR at receiver and thus a lower bit error rate. In combination with adaptive transmission, it can achieve a high spectral efficiency. However, there are two downsides to using a high transmit power. The first one is that it will drain the battery of the user. The second one is that by behaving selfishly, it can create interference for the other users. This is shown in the two pictures on the bottom. The picture on the left shows the case of inter-cell interference, where we have two users, one on the left and one on the right, transmitting to their base stations over the same frequency band. The signal from the user on the left to its base station is affected by interference from the other user on the right. This is shown with the dashed arrows. If the user on the right is transmitting with a high power, the interference signal could be stronger than the useful signal. This will prevent the base station from recovering the signal of the nearby user. There is also intra-cell interference, for instance, in CDMA systems. We have two users, one close to the base station, one far away. Because the codes of the users may not be perfectly orthogonal or due to timing offsets, there exists residual multi-user interference. If the nearby user transmits with very high power while the faraway user does not, then the multi-user interference from the nearby users will drown out the signal from the faraway user. So in both of those cases, it is not always advantageous to transmit with a very high power from a system perspective. To analyze how users should allocate their power, it is useful to study the signal to interference and noise ratio. Let's suppose we have three users that each transmit with their own power, P1, P2, and P3, to a common base station. For the base station to recover the signal from a certain user, user I, it needs to have an SINR greater than some threshold called the capture ratio gamma I. This gamma I can vary user by user. So the condition for successful reception at the receiver of the transmissions of each other user is given by this expression. The useful signal power, which contains the transmit power and the amplitude of the channel squared, divided by the interference plus noise power, should exceed the threshold. So the users, knowing the channels and knowing the threshold, should adapt their transmit power. It is clear that an optimal transmit power should satisfy this constraint with equality, because if the equality is not met, then a user can reduce its transmit power. Consider the following simple problem below, with 2 users and 2 base stations. As a simple problem, I ask you to write down the SINR inequalities for each of the links, and plot those inequalities in the coordinates of the 2 transmit powers for the users. From that, try to find the optimal power levels. I invite you to pause the presentation and come back after having solved the problem. So the scenario shown on the right, there are 2 transmitters, S1 and S2, 2 receivers, R1, R2, and the channels, G11 from transmitter 1 to receiver 1, G12 from transmitter 1 to receiver 2, G21 from transmitter 2 to receiver 1, and G22 from transmitter 2 to receiver 2. The SINR constraints for each of the links is as follows. So from the link from user 1 to receiver 1, it's given by this requirement. This is the useful power, the interference, and the noise. On the right-hand side, we have the threshold for user 1. So note that the interference depends on the link from user 2 to receiver 1. Similarly, we have an expression for the SINR for receiver 2. By replacing these inequalities with equalities, we can draw the following figure. So on this figure, the x-axis shows P1, the transmit power for user 1. On the y-axis, P2, the transmit power for user 2. By replacing the inequalities with equalities, we obtain lines. So one of the lines is this one. This is the equality constraint for user 1. Similarly, we have a line for user 2, which is this one. If we now replace the equality back with an inequality, we find for user 1 a half plane, so this side. We can do the same for user 2 and we find another half plane. The intersection of those 2 half planes is the shaded area shown here. So for every point in the shaded area, both of the constraints are met. We can recover the signals from both of the users. If we operate, for instance, here, the constraint is only met for user 1 but not user 2. If we operate here, the constraint is met for user 2 but not for user 1. But whether we operate here or here or here, the constraints for both users are met. However, we want to have the lowest possible transmit power, and this gives this unique point. This is the lowest transmit power that satisfies the constraint, and it has to lie on the intersection of the 2 lines, where each line is found by replacing the inequality with an equality. So the point P1 star, P2 star is the optimal point. You can then generalize this to a multi-user scenario with more than 2 transmitters. We can do the same for an arbitrary number of users. So let's say for user I, we have the SINR threshold, the transmit power, and the power of the interference plus the noise divided by GII. So this is just the same SINR constraint as before, just written slightly different. Here, the sum goes over all the users, j different from I, that can cause interference. We can write this in a matrix form in the following way. We know that for the optimal point, this inequality will be replaced by an equality. This kind of problem can be solved in a distributed way using the Foschini-Miljanic algorithm. What we do is we initialize the transmit power for each user to some random value and then run the following iterative algorithm. We choose small numbers ki for each user. Each user will then do the following. It transmits with its power and then measures the interference. So it can measure this interference. It will then adapt the power accordingly. So the next iteration for its power will be the previous value times 1 minus ki, so this is almost the previous value, with a correction factor that depends on its SINR threshold and the observed interference. Under some technical conditions, this algorithm can be shown to converge to the optimal value. Now, not all networks are cellular networks. There is also something called random access. This is used, for instance, in Wi-Fi communication. Random access is suitable, for instance, for bursty traffic, and when you have more users than channels. There are several common protocols. The first one is called Aloha. Under Aloha, we here have different users, A, B, C, D, and time. And a user will transmit a packet as soon as it has a packet to transmit. However, when two users are transmitting at the same time, this will lead to a collision. In slotted Aloha, performance can be improved a little bit by considering slotted time. So when I have a packet to transmit, I will wait to the next time slot and then transmit. A more powerful variation is carrier sense multiple access. For instance, the p-persistent algorithm. Here, a user, when it has something to transmit, it will sense the channel. So it will listen to the channel. If the channel is occupied, it will wait. If the channel is free, then it will transmit with some probability p. There is also a variation called CSMA. CA is carrier sense multiple access with collision avoidance. On the right-hand side, we show a flowchart of CSMA-CA. So here, once we have a packet to send, we listen to the channel. Is the channel available or not? If the channel is not available, we wait for a random backoff time. Once the channel becomes available, we are sending a request to send signal. We then wait to hear back from the receiver with a clear to send signal. If the clear to send signal was not received, that means someone else was transmitting at the same time, and we go back to waiting. If the clear to send signal was received, then we transmit our data. And then we end, and we go back to the beginning, waiting for more data to be transmitted. In many applications, RTS and CTS are not used, and we go directly from this yes decision to transmitting the data. This ends the multi-user communication lecture. You should be able to describe differences between uplink, downlink, multiple access, and random access, mathematically describe TDMA, FDMA, and CDMA. You should be able to design and analyze multiple access schemes for a given scenario and compute SIR and SINR values.